Can we start?
Yes.
So, good morning. This is the session in which we engage with the compaction test in the laboratory. So, Proctor was the inventor of this test, and it is a technique that enables us to understand properties of soil that are supposed to be used in embankment for construction of embankment dams, so road works, railway fields, and etc. So we are now interested in understanding the behavior of this unsaturated soil. We explained that last time that when the soil is not saturated, very complicated things happen there because of the suction of water, the effect of capillarity that increase in principle the strength of the material, because there is a kind of effect of suction is to increase actually the micro effective stress inside the soil, and because of friction between grains, even if there is no external load, you have the soil does acquire some strength. So, and now today we are doing this experiment with the help from George Nikitas. George is our technician in, he's also a PhD student, he's also a technician, he has two hats, and then he did prepare carefully all the tests for today. And we basically are following the notes that you have, but this year I would like to introduce some small change in the technique, just to make the experiment probably more interesting and complete. So first thing to say is to call the hello. The first thing to say is, is my voice okay for the coordinator? You should speak.
I hope so.
Speak up louder.
A bit louder.
Okay, a bit louder. Okay. The basic plot is a plot in which you have an x-axis, the water content W, and the y-axis gamma D. Gamma D is a gamma dry of soil. And in the x-axis, we have W. So today, eventually, we will have at least for one single curve, at least 4 points, let's say 4 experimental points like this. And then you will be part of your coursework. We present your guess for matching this experimental point with one curve. So don't use, please, Excel Streamline, because it is the worst way to process the data, because Excel will start doing funny stuff like that. We need to have a reasonable and line that you can draw by hand. Maybe it's better than using Excel. Okay? So basically what I want to do is that you have 4 water content. Let's say we start for 4%, 4%, I think, yes, 8%, let's say 12, let's say 16. It's a bit risky always, the experiment, because maybe that water content is optimum is outside this range, but I think this would be the range in which we should find our optimal water content, and gamma D max, of course. And this here, I want you to deal with this energy, E1, one certain experiment, but also I want, because George prepared two molds. In this other mold, we can use larger energy. Or maybe we can use the same Proctor's basic with a double number of blows. We will see now in 1 minute what we can decide about this. What I expect from this experiment to find some gamma D max here for this energy as correspondent to this value of W optimum. But then when we go to increase the energy, as we mentioned last week, we should find something like that for E2, energy, specific energy E2, with E2 larger than E1. And this point should move in this direction, the maximum point, or to the left. So the new gamma W max for that energy should be is larger, but the corresponding value of W optimum should be less. Maybe you don't find this because it's very sometimes complicated, but at least this is our aim. Of course, we should be honest, and as always are in the laboratory, we should just process what we have. Maybe we don't find this, but this is what we expect. In your coursework, please remember this equation here about the value of gamma D, gamma W, divided 1 plus 1 of the GS. This equation, how do we call this equation here? What does this equation represent? This is a saturation strategy. So if you have saturated soil, okay, soil is saturated, at each water content, this is called GS, at each water content, we have a value of gamma D, because gamma W is gamma water, is 10 kilonewton roughly per cubic meter. GS is fixed for the soil, it doesn't depend on the void, because GS is specific gravity, it's a ratio between the mass of the soil part of the grain and the volume of the grains. So let's say if I have here, I don't know, 2.7 is non-dimensional number. You have here gamma W put here, this dimension is 10 kilonewton per cubic meter, and W is my parameter independent variable. For each value of W, which is 0.1, 0.2, you can get the corresponding value of gamma D. And you should find here the saturation curve, which is curved like this. So question, what do you expect here, which is the value you're reading here on the y-axis? Someone can have a guess on this? Which gamma D I have here?
100.
Sorry?
100% saturation. 100% saturation.
I have here W put 0, I have gamma D equal GS times gamma W. Therefore, it is, by definition, you know this? GS, unit volume weight of solid. Definition, GS times gamma W. It is the definition of GS, if you want. So, interesting enough, this when you have a soil, you have this value here is known, because exactly is the value of the gamma S of solids. Okay? So, what is the symptom of this curve? So when W tends to minus 1 over GS, this gets infinite. And when this value is infinite, W tends to 0. So also I have two asymptotes. I don't have the space for it. One is this one, and this is, of course, is minus 1 over GS. Okay, good. And this goes to 0 when other asymptote, when W is infinite, gamma D tends to 0. I want to have this stuff clear because I want to present you these discussions in your coursework, because it's a matter to, if you don't have a clear, if you don't show, for example, the asymptote in your coursework, of course you are losing, of course they're not failing, but maybe you cannot get, can have 100% for the reason, can have 2 or 3 marks less, because I want to address properly the meaning of saturation curve. And the last point is, which zone is this one? How did we call this zone last time?
It's not possible.
Not possible zone, perfect. This is an impossible zone. So as I mentioned, if we have a report from the laboratory and then we put a number here, please don't pay the bill, because that data are fake. They cannot be above that curve. Okay? Okay, now, you have some guide in your, George is a master in this, can help us to do this. Every time we have problem, of course, because we have two ways of introducing water content. Water content is something that is complicated here, because we, for the beginning, we start with an idea of our amount of water to add to the soil. But then we are going to take some specimen in order to put in the oven and check the water content at each step. And then we have some approximation. Try to explain better this point. So, the first thing is to do is to understand this, so to remember that the relationship between unit weight of volume gamma and gamma W, and gamma D, sorry. Gamma and gamma D is 1 plus W is the factor of gamma D in order to get gamma. Gamma is the unit weight wet of the soil, this is the unit weight dry of the soil, this is water content. So, of course, when we have an saturated soil, we have this relation of, okay, let's say at the beginning, we can write this also in terms of course, not in terms of specific volume, but in terms of real volume. So I can write here, W is the weight of some amount of soil, equal the same amount of weight dry times 1 plus W. It holds as well. This is useful, why? Because if we want to, if you want to put the first value of mass of water in our team, we should of course start from the knowledge of the soil, which George put in the oven one or 2 days. It's totally dry, and we are assuming here, George, correct me if I'm wrong, that the water content here is 0. Okay? It's nominally 0. If it's 1%, we don't care. Let's say it's 0. Therefore, if this is the weight dry, it's very easy. In principle, we focus on certain mass of soil to calculate the 5% of this, and therefore the 4% for the 8, 12, and 16, because you should repeat 4 times the test. And each time you add this. But another, when you finish, as I think you read your note, when you finish complete one point, you move to the other point. When you finish one compaction, you should recover 3 small specimens from the same sample. So because we have 3 strata, 1 specimen per strata, put in 3 tins and put in the oven to check then the water content at which really you compacted the soil. You do an average between the three values. And you will find some discrepancies between this number and the nominal number that you introduce with exercise compared using the initial dry mass of the soil. So what we, in principle, if you want to be more precise, what you can do is using this equation. Each time you have, at the beginning when you have to set up the amount of water in the tray to prepare that water content, you can weight your wet material, then you can, you know how much is your value of gamma d, okay? And then you can work out W. But the problem is that you don't have your gamma d here, because you have the soil, you cannot put the soil in the oven. So how you can work out this? I want you to think about this a bit. So you want to rely on this initial guess or not? So in your small time available, maybe the best thing to do is to rely on just on this initial value of mass of water. So 4% of water, 8% for water, 12% and 16%. Using the initial mass of the material that you have here. So we have basically here, I think 2 kilograms here. How much we have? 2 kilograms?
Yes, 2 to 3.